Pastorfide.
And together we are the kid number 10 from grade 12 STEM Philippines.
In Activity 1, the function of the serial monitor is to display messages. When connected to the Arduino Uno, it shows the message, "Hello, student." In Activity 2, we started to do wirings and use a temperature sensor to measure the room temperature. The serial monitor displays the temperature readings detected by the sensor. In Activity 3, we used a button, and the serial monitor shows whether the button is being pressed. In Activity 4, we used an LED, and the serial monitor served as a remote control. Typing 1 turns the LED on, while typing 0 turns it off. Lastly, in Activity 5, we use a photoresistor and our phones as flashlights. The serial monitor shows the light level when the flashlight shines on the photoresistor. During our serial monitor activities, we faced issues like wiring errors, unstable readings, and false triggers. We fixed this by checking connections, setting the correct baud rate, and adjusting the code. Using components like the LM35, button, LED, and LDR, we learned how this can be applied in smart systems and improved our troubleshooting and coding skills. In Activity 1, we tested a simple distance measurement setup. The ultrasonic sensor readings appeared on the serial monitor, showing how sound waves can be used to detect objects at different distances. In Activity 2, we connected an ultrasonic sensor, or the HC SR04, to the Arduino Uno and added a 16x2 I2C LCD to display the results. In Activity 3, we built a circuit for an obstacle detector. When an object comes close, the LED turns on. And lastly, in Activity 4, we created the parking assistance system using 3 LEDs, the green, yellow, and red LEDs, and the buzzer. As the object comes close, the LEDs change from green to yellow to red, while the buzzer beeps faster. We explored how ultrasonic sensors measure distance and detect obstacles using Arduino. We displayed readings on the serial monitor and LCD, built an obstacle detector with an LED, and created a parking assistant with LEDs and a buzzer. Challenges like unstable readings and wiring errors were solved by checking connections and adjusting delays. These systems can be applied in parking sensors, obstacle avoiding robots, and smart waste bins. We use an IR sensor to detect black and white surfaces. The serial monitor showed light surface detected for white and dark surface detected for black. We fix unstable readings by adjusting distance in wirings. This can be used in line following robots. We use an ultrasonic sensor to measure distance and display results on the serial monitor. We solved the unstable readings by aligning the sensor properly. This is useful in obstacle detection systems. In Activity 3, we added a 16x2 LCD to show the distance measured by the ultrasonic sensor in real time. We fixed display errors by checking wirings, and this can be used in digital measuring tools. Activity 1, we use a push button and the MOSFET to control a DC motor with an Arduino. When the button was pressed, the motor turned on. When released, it stopped. We face wiring polarity issues which we solve by checking connections and grounding properly. This setup can be used in motor control systems like fans, conveyors, and small robots. We use a potentiometer and MOSFET to control the speed of a DC motor through PWM signals from the Arduino. Turning the knob changed the motor speed from slow to fast. We use unstable speed control at first, which we solve by securing the potentiometer connections. This setup can be applied in fan speed controllers, electric vehicles, and robotics systems. In Activity 1, we controlled a DC motor's on and off state using an L29 3D motor driver and Arduino. The motor ran for 1 second then stopped for 1 second repeatedly. We faced wiring confusions with the L29 3D pins, which we solved by carefully following the pin layout. This setup can be applied in simple automation projects, conveyor systems, and basic robotics. We controlled the DC motor speed using PWM through the L29 3D motor driver and Arduino. The motor gradually sped up and slowed down, showing how digital signals can mimic analog control. We face uneven speed changes at first, which we fixed by adjusting delay timing. This can be applied in fan speed controllers, electric toys, and motor-driven automation systems. We controlled the motor's direction using two Arduino pins connected to the L29 3D motor driver. By changing the logic levels, the motor spun clockwise or counterclockwise. We faced wiring mix-ups at first, which we solved by checking pin connections. This setup is useful in robots, conveyor systems, and automated machines that require bidirectional movements. We used two push buttons with the L29 3D motor driver to control the motor's direction. Pressing one button made it spin forward, and the other made it spin in reverse. If no button was pressed, it stopped. We encountered button bounce and wiring errors, which we solved by securing connections and using pull-up inputs. This system can be applied in robotic arms, motorized vehicles, and manual control panels. We controlled both the direction and speed of a DC motor using two push buttons and the potentiometer connected to the L29 3D motor driver. The button set the direction, while the potentiometer adjusted the motor speed through PWM. We faced unstable changes, which we fixed by tightening connection and calibrating the potentiometer. This setup can be applied in remote-controlled vehicles, adjustable fans, and robotic systems.
Good day everyone, I am Andrea Rizabelle Aquino, the leader of Kit number 10, and here are my group members.